All right, let's dive into something that honestly powers pretty much every single app and website you use, but it's almost totally invisible: database design. You can think of it as the hidden blueprint for information, and, well, getting it right or wrong has some huge consequences. So let's untangle this whole thing.
I know, it's kind of a weird question, right? I mean, data is just data, it's facts. But what if the way you're storing those facts is creating these hidden cracks in the very foundation of your system? What if your data is quietly lying to you, or even worse, just waiting for the right moment to completely fall apart?
So, we're going to kick this off a bit like a detective story. Imagine we've just arrived at the scene, and at first glance, everything looks perfectly fine, totally normal. But there's a flaw, a hidden glitch that's causing all sorts of chaos behind the scenes, and our job is to find it.
Okay, so take a look at this. It's a super simple table, right? It's just tracking which student is in which course and what room that course is in. You can see student 111 is in CS 145, and that class is in room B01. Seems pretty straightforward, doesn't it? Do you see anything wrong here? Anything at all? Aha, here's the problem. The fact that course CS 145 is held in room B01 is repeated. It's repeated for every single student enrolled in it. So if 1,000 students take this class, that exact same piece of information, CS 145 is in B01, is stored 1,000 times. That, right there, that's our hidden glitch. And this repetition, it has a name. It's called redundancy, and it is the absolute villain of our story today. Now, it might seem harmless, maybe just a little bit of wasted space, but trust me, redundancy is the root cause of some really, really nasty data problems. In the world of database design, these problems have a specific name. They're called anomalies, and these are not just minor bugs. Oh no, they are dangerous glitches that can totally corrupt your data, make it inconsistent, and sometimes even cause you to lose information for good. And these are the three main culprits. First up, you've got the update anomaly. Let's say CS 145 moves to a new room. Now you have to hunt down and change every single row for that course. If you miss just one, your database is literally telling two different stories about where that class is. Then there's the insert anomaly. What if you want to add a new course, say CS 229 in room C12? Well, with this setup, you can't. Not until at least one student signs up for it. There's just no way to store that fact by itself. And finally, the scariest one, the delete anomaly. If every student in CS 145 drops the class, all the rows that mention it just vanish. And you know what vanishes with them? The fact that CS 145 was ever in room B01. Poof! That information is just gone forever. So, how in the world do we prevent all this chaos? Well, we need to set up some rules. We need a proper, formal way to describe the relationships hidden in our data so we can build a structure that isn't so incredibly fragile. Now, our main tool for this is something called a functional dependency. Okay, I know it sounds super technical, but the idea is actually really simple. It's just a rule that says if you know the value of one thing, you automatically know the value of another. It's that simple. If you know X, you must know Y. For example, if you know a unique employee ID, you have to know their specific name. That's a functional dependency. And this shows the difference between a good rule and a bad one perfectly. The rule on the left, employee ID determines name and phone, that's solid. It makes sense. There's only one name for employee E9999. But the rule on the right, position determines phone, that's a weak rule. Knowing someone is a sales rep doesn't tell you their specific phone number, right? There could be dozens of sales reps. So our goal is to find these good, strong rules and build our database around them. Okay, so we've found the problem, redundancy, and we have our main tool for fixing it, functional dependencies. That brings us to the next step, the art of tidying up. This is where we look at the actual process for fixing this mess. This whole tidying up process, it has a formal name. It's called normalization. It's really just a systematic way to organize your data, using those rules we just talked about, to get rid of redundancy and to eliminate those nasty update, insert, and delete anomalies. You can think of it like a series of quality checkpoints for your design. And these checkpoints are called normal forms. You've got first normal form, second, and so on. As you can see here, each level, each form is a stricter, more tidy version than the one before it. As you move your design up to a higher normal form, you're systematically killing off more and more of those potential glitches. Now here's a super important point.
You don't always have to go all the way to the end. In the real world, for most apps, the goal is to reach what's called third normal form, or 3NF, or maybe Boy's Cod normal form, BCNF. These levels solve the vast majority of the problems you'll ever run into, and they're still practical to work with. The goal isn't some kind of theoretical perfection, it's just a solid, robust, and reliable design.
Which brings us to the big payoff. It's time to go back to our original crime scene and actually apply all these ideas to fix it, once and for all.
And here it is again, our messy, redundant little table. Remember the functional dependency that's causing all the trouble? It's that course determines room. But that rule is all tangled up with the information about which student is in the course.
So, the solution, using this process of normalization, is to split or decompose this one big table into multiple smaller tables. Each new table is going to be organized around one single clear rule. It's time to untangle the data.
So here's our first new table, and it is beautifully simple. Its one and only job is to track which student is enrolled in which course. That is it. Notice, no more redundant room information anywhere in sight.
And here's our second table, which also does just one job. It tells us where each course is located. The fact that CS145 is in B01 is now stored exactly once. This is just so much healthier, so much cleaner of a design. So the big question is, after all that work, after splitting the table, did we actually fix anything? Is this new two-table design genuinely better than what we started with?
Oh yeah, absolutely. Let's just run down the checklist. Redundancy, gone. Update anomaly, solved. If CS145 moves, we change it in exactly one spot. Insert anomaly, solved. We can add a new course and its room anytime we want. And the delete anomaly, solved. If every student drops CS145, their enrollment records disappear, but that second table, the one that knows where the class is completely untouched. Every single one of our original problems is fixed. Now, this all seems really neat and tidy, right? Almost mechanical. You just find the rules, you apply the process, and you get a perfect result. But there's one last really crucial piece to this whole puzzle. And this quote right here, it gets to the heart of it. The theory of normalization, it can give you clues. It can show you a few different mathematically valid ways to split up your tables. But the theory itself has no idea what your data actually means. A human designer has to look at the different options and choose the one that makes the most sense for what the application is actually trying to do in the real world.
And that really leaves us with this final thought. Good database design isn't just a science, it's also an art. The rules, the normal forms, they give us a map to a much better place, a place without all that redundancy and those dangerous anomalies. But at the end of the day, it's still up to us, the designers, to use our own wisdom and our understanding of the real world to actually read that map and choose the best path forward. Thanks for watching.